Okay, this system has been crashing on me again, and I am really hoping Satya Nadella will screw up his investments and lose a few $1 billion for making me do this so many times. Okay, Microsoft. Disaster. Okay, so we introduced the idea of tipping elements, tipping points, and we said for any system, feedbacks are the most critical things, whether it's the human body, where if you break one thing, it's going to lead to many other problems, or the Earth system, where there are these feedbacks that we talked about when we talked about the processes, right? So you expect that if there are feedbacks in the system, then the key question will be whether there are interactions between these tipping elements which can accelerate the other one or another tipping point, few other tipping points, and lead to what is called the domino effect, where things just begin to collapse. So this paper does some modeling of the risks of these tipping elements, estimates the temperature warming, global mean temperature increase, which can tip one or the other, and how they interact with each other. So here is the initiator of tipping cascade in red, and occurrence in tipping cascades. So you can see that there are positive feedbacks. For example, disintegration of the West Antarctic ice sheet would raise sea level, which would have a positive feedback, initiating a tipping cascade onto the disintegration of ice sheets through the AMOC and Atlantic meridional overturning circulation, and that would have positive feedbacks to weakening of the Atlantic meridional overturning circulation by putting freshwater cap where evaporation is able to create larger salinity and sink the water. So if you put a lot of fresh water through disintegration of Greenland ice sheet, you can weaken that, but that would have a negative feedback because you would reduce the amount of heat being brought in from the tropics and reduce the original warming. You would have then a change in precipitation, which would affect the dieback of Amazon forest, which remains uncertain, could be positive or negative. So there are various percentages shown here in terms of occurrence in tipping cascades, depending on which tipping initiator of the tipping cascade happens. So the numbers are shown here: 65%, 29%, 13%, 28%, and so on. I'm not going to dwell into the details of it, because when there is modeling involved, there are assumptions involved, which means there are uncertainties in the assumptions and uncertainties in these estimates. So you should take them as storylines or what if scenarios or probabilities, and just focus on the processes for our interest here in an introductory course. So weakening AMOC would have a positive feedback to the Southern Ocean heat accumulation. So you would, if the AMOC weakens, you are transporting less heat out of the heat accumulation, and you will have a negative, an unknown feedback to the salinity gradient increase and fast advection of freshwater anomalies, which are detailed processes of which water mass actually gets transported in the Atlantic meridional overturning. So it's weakened, it's not disappeared, then you will change these kind of issues, the mixing in the Southern Ocean and the inundation of the Indian and Pacific Oceans, conversion to surface water and back, and so on. So there is a destabilizing effect or positive feedback, and a stabilizing effect or a negative feedback, and unknown directions at this point. Okay, so I will leave it with that kind of descriptive point, and you can look at more dynamic system kind of calculations. Basically, these are dynamic systems, are nonlinear systems where slight change in the initial condition can take you to very different directions, like the graph we are looking at here. You can also look up nice animations or simulations or videos of the double pendulum, for example, to see how wildly it oscillates when you have two oscillating elements tied together, because the two-body problem is very, very non-linear. So here we are looking at some measure of the state of the tipping element, and it goes from the stable baseline regime. Global warming is going to take you towards a tipping point, and that's at this point here, that's the initiator of the cascade. So the tipping by coupling to other elements is going to reduce the time and the global mean temperature at which the combined tipping will happen, as opposed to just the global mean temperature increase driving one tipping element. So this is what is called unstable manifold, or the sudden bifurcation of the system. You can see that there are two possible solutions here. Whether you get from there to there or through here depends on various things. So this is the stable transitioned regime, and this is the unstable manifold, and here is another stable transitioned regime. Just get a sense that when you have multiple tipping elements, one can start because of, let's say, the global mean temperature increase or sea level rise hitting some threshold, then that will trigger another tipping point, and then they begin to interact with each other, and this is kind of the domino effect where you quickly transition into the unstable manifold. Okay, so here you are in terms of model time, which is an arbitrary unit in the forward integration, and the state of the tipping element again. So you have the Amazon rainforest, which is not doing much here, or the baseline regime. The AMOC is jumping the tipping element, but it can combine with West Antarctica and can very rapidly transition to a unstable state of the tipping element. So you go into a transitioned new regime. So you go from, let's say, glaciated planet like we have now to a completely deglaciated planet, in which case, for example, the sea level rise would be higher than more than 300 feet, or yeah, let's check and make sure. Maybe it's 300 meters. I keep forgetting. Okay, so West Antarctic and Greenland together, so Greenland can go tipping by itself over the baseline regime, and because of the various processes that we already talked about, Greenland and the Arctic ice may be heading towards their tipping points, and it's always difficult to know how close you are to this unstable transition point, and then only you can know how close you are to cascading interactions with other tipping points and so on. So uncertainty is large. These are somewhat heuristic arguments, possibilities in the system. Nodes in the model network of interacting tipping elements. For each tipping element in the network that we saw in figure 1, a range of critical temperature limit is known from a review of the literature. So these are building on previous heuristic arguments. Within this temperature range, the tipping element is likely to undergo a qualitative state transition. Qualitative state transition, so you have to always remember that. So tipping elements are Greenland ice sheet, West Antarctic ice sheets, because there are many, AMOC, Atlantic Meridional Overturning, and the Amazon rainforest. And the estimated limits for qualitative transition are, this is the global mean temperature rise over the pre-industrial baseline, let's say. Greenland is in the range of 0.8 to 3.2. That gives you a sense of just how uncertain we are. West Antarctica is 0.8 to 5.5, even a larger range of temperatures. AMOC is 3.5 to 6, so AMOC requires much higher warming to hit its tipping point, and Amazon forest is 3.5 to 4.5, and I'm not even sure the ranges are incredibly well constrained by themselves, and then imagine interactions between them. So here we are looking at critical temperature again, going from 1 to 8 degrees centigrade warming above a baseline. Tipping elements with their ranges, Greenland, West Antarctica, AMOC, and the Amazon. And we are looking at the interaction strength between them, including the destabilizing feedback and the stabilizing feedbacks, looking in the, again, arbitrary unit as defined in the model. So Greenland here starting at interaction strength of 0 and critical temperature range. So you can see that there is a large range, and West Antarctica has a range here around 3 to whatever degrees centigrade we said before, so less than a degree to 5.5 degrees, and then the interaction strength remains increasing, but the critical temperature at that point is already reached, and Greenland has a much larger range in terms of critical temperature and its interaction strength. So the relation here is a growing temperature, critical temperature, because Greenland can cap the AMOC and have a cascading feedback with AMOC, Southern Ocean heat storage, and West Antarctica, and so on. Okay, so here is the same thing with AMOC and Amazon forest, but just what do you want to get out of it? The idea is basically to be sure that you understand that there are feedbacks in the system and there are tipping points. These are potential tipping points. We don't know exactly when they will occur, so we have a large range of warming which can tip them as estimated from the best knowledge we have. And when you have multiple tipping elements in the Earth system, you must account for the fact that they can interact with each other with stabilizing and destabilizing feedbacks. So you want to know if there are potential domino effects in the climate system where one tipping element will get triggered and then it will begin to affect other tipping elements in a positive or negative way, and can either take you to a stable new regime or through the unstable manifold, as we said, where transitions can be very rapid and unpredictable. Okay, so I will leave it there. You can read more in the paper that I cited here.